Okay, so I'm recording now. So this is a very quick review. Vibrations. Vibration is basically a motion about equilibrium. So a motion that goes on like this, like the motion of a car, is not vibration, but the motion of the car on the road, like vertical motion of the car on a road, is vibration because it's something about the equilibrium position and it's a small motion. The typical motion of a system is like a mass and a spring. You pull the mass and leave it, and it vibrates like this. This is the vibration. It goes back and forth, and that is what we call the simplest form of vibration. We define the periodic motion, in which the motion repeats itself with a period t, and the frequency is the inverse of that period. F frequency is 1 over t, and that is cycles, that is cycles per second. That is how many periods are taken in 1 second. But we in vibrations don't use that. We use the circular frequency, which is this omega, okay? And don't call this W, this is omega, okay? The Greek letter omega. Omega is the circular frequency, which has a unit of radians per second, and this is what we will be using because you have to substitute always it into sines and cosines, and therefore you have to use that omega there. Omega is simply not 1 over t, but 2 pi over t, and omega is 2 pi times the frequency. Frequency is an important variable, concept and variable. Now, a sine wave is a sine omega t is the simplest vibration function, let's say. Okay, a is the amplitude, omega is the frequency. And between two sine waves, there might be a phase difference, phase shift. As you see, if you have x1 and x2 with the same frequency omega, there might be a phase shift of phi, which shows how the motion leads or lags the other motion or other signal. Okay. Now, very important are harmonic functions, sines and cosines. Okay, they are the most commonly used functions in vibrations. So it's you either sine or cosine. They are more or less very similar functions. Only difference is that they have a phase difference. Okay, there is a phase difference of pi over 2 between sine and cosine function. There is not much different other than that. Otherwise, we started the free vibration. Well, we divide the vibrations into free and forced vibrations. Free vibrations are vibrations due to initial displacements or initial velocities. So you take a mass spring system, you leave it, and it starts oscillating like this. Or if you take a pendulum, you move it, it oscillates just by itself. There is no forcing here. And the frequency of the free vibration is called the natural frequency. And it is dependent on the parameters of the system, as we will see. It is, for example, for this system, it is for the mass spring system, it is root k over m. For the pendulum, it is root g over L, as we will be seeing shortly. Our forced vibrations, the second part, it is due to external forces. For example, you might have a sinusoidal forcing, which is very important for us. We call it harmonic forcing. In the case of harmonic forcing or periodic forcing, we encounter a phenomenon called resonance. And resonance happens when the frequency of forcing omega coincides with the frequency of natural frequency of the system. So if omega is equal to omega n, we will have resonance and the amplitude of vibration is going to grow up indefinitely. Resonance is something we don't want. We try to avoid resonance, and it is very important in vibrations that we avoid resonance. Okay, other than that, we started the kinetic and potential energies. We have mechanical systems. Mechanical systems can be, translational. These are translational. Maybe we should say translational, and these are rotational. You might have a combination of them, but you can separate it like that. We basically use F equals ma or m equals I alpha, or we use the energies, kinetic potential. I talked about this, so I'm not talking about it again. The damper is a device that dissipates energy. It is used to model the energy dissipation in the system. Well, you can use dry friction as well, but dry friction is more difficult to model. So damper is an easier model, so that's why we use it. The viscous damper, maybe I should say in parentheses here, viscous damper, so that the force is proportional to the velocity here. The damping force is proportional to the velocity or relative velocity. And the power dissipated is, as you can see, it is the V times relative velocity. Sorry, force times relative velocity squared. Sorry, V times relative velocity squared, which is force times relative velocity. So we want to first obtain the differential equations. Now the vibrations are defined by differential equations, okay? Differential equations is a class you take in the second year, and you wonder why we are taking this, but they are extremely important. In all engineering, we model systems by, not by algebraic equations, but with differential equations. Differential equations are very fundamental. So we have to know how to form them and then know how to solve them. Here we are talking about how to form them. That is how to obtain the differential equations. For vibrations, we have two basic methods. One is Newton's laws. You just write sigma F equals ma, sigma m equals I alpha for each mass and inertia. Okay. From which you get the differential equation. Or another method is, this is valid only for 1 degree of freedom systems, okay? If you have a single mass, as I will explain, you write the kinetic total energy is equal to kinetic plus potential energy, and then you take the derivative of that energy. If there is a power input, the derivative of the energy is simply should be equal to the net power input, which is the power input minus the power dissipated. So you can find equation of motion like that. And I gave you an example last time, mass spring damper system with a forcing on it. So the summation of all forces on the mass, we write the free body diagram, draw the free body diagram, is equal to, there is the force, there is the spring force, there is the damping force. The forces in the y directions don't matter. We are looking at the x motions. So they are equal to mass times acceleration, which is mx double dot. So if you rearrange, you get mx double dot plus bx dot plus kx equals f of t. Now, one thing I want to make you pay attention are these plus signs, okay? In a If for a stable vibrational system, all these signs are all positive. Okay, they have to be positive. Otherwise, the equation of motion you have is not going to be a vibration, but it is going to just blow up, basically. So all the signs must be positive, and that is a check. You shouldn't be getting out of your equations negative signs in the context of vibrations. In the control systems, that might be possible, but that's another matter. We will talk about it next semester in the controls class. So for the same system, we can do the energy method. Power in is the force times the velocity. This is velocity, as you know. Force times velocity is the power. And this is the force times the velocity squared, as you see. Sorry, not force. Yeah, sorry. It is force times the force, damping force times the velocity, rather. And if you substitute everything in, you have x dot terms in all of the terms, so you cancel them, and you get the same equation as you should. Okay, there shouldn't be a difference, obviously, between those things. So this is where we had stopped the last time. Let me give you one more example. So that is what I had given, which is the simple pendulum. Supposedly. Like the pendulum used in the mechanical clocks. Well, that is something ancient, but so this is an interesting device like this. This is an angle of theta. The pendulum has a length of L. It has a mass of M. The rod is, we assume that this is massless rod. That is, the mass is negligible. There is gravity here. And there might be an external torque acting on it. So we will be modeling this, try to find the equation of motion using Newton's method and the energy method. Let me use Newton's method now. We start by drawing the free body diagram. We take it as a whole. We remove it from its surroundings. So there are the reaction forces, but let me first draw the pendulum. In the pendulum, there is a force of mg, as you know. There are the reactions Rx, Ry, which are not very important for us. This point is, let's say, is point O. And we have to pay attention to the geometry. This is theta, this is L. So this distance is L sine theta. Okay. Now, in order to find the equation of motion, there is also the external torque, obviously. So we take moments, let's say that counterclockwise, moments about point O. And when you take moments, the T of T is there, it's counterclockwise. And then you have the mg term trying to create a moment about point O, which is minus, it is clockwise, so it is mgl sine theta. mgl sine theta is the moment. This is the total forces. This should be equal to I times alpha. But what is I here? The rod is massless. There is a mass here, which is at a distance of O from here. I should be, by parallel axis theorem, as you might remember, is ml squared. So it is ml squared alpha, but alpha is theta double dot, second derivative of theta. So the equation of motion is ml squared theta double dot. Now mgl goes to this side, plus mgl sine theta equals t of t. This is the equation of motion. Well, there is something strange about this. First of all, this sine term makes the equation nonlinear. We would like to make it, we have a linear equation so that we can solve it. So we do an approximation here. So we will do for small theta, we can say that sine theta should be equal to what? Is approximately equal to theta. But theta should be in radians. That's important. Okay. Well, almost up to 30 degrees, sine theta is close to theta. Sine theta is 1/2. Sine 30 is 1/2. And 30 degrees is close to 1/2 radians. A little bit less, but it's very close. Up to that, it is okay. So the equation of motion is basically ml squared theta double dot plus mgl theta equals t of t. And this is the inertia term, as you see. This is the spring term. There is no spring here, but this is the restoring effect of, let's say, gravity. And this is the external torque. So this is the approximate linear equation of motion. So this is linearized. Equation of motion. For equation of motion, I will use EOM in short. Okay. Okay. Now let's try this is the Newton's method. This is what we get out of this. So let's use the energy approach. We will obviously get the same thing, but let's see. You don't have to write the forces anymore. You have the pendulum, but you have to know the kinematics of the pendulum here. Now this is L, this is also L, supposedly. The whole thing is L. Okay. Doesn't look like it, but it is. But you have to assume that. So this is L sine theta, this is theta. This is L sine theta. This is L cosine theta. And this part, this whole thing is L, so this part is L minus L cosine theta. Okay, because the whole is L. Okay, we need this for potential energy. And also the velocity of the pendulum, when it is theta, the velocity is equal to L theta dot. Okay, it is tangent to the path of the pendulum. So we need to write the energies here. The kinetic energy is 1/2 m v squared, which is L theta dot squared. That is equal to 1/2 m L squared theta dot squared. Okay. All right. The potential energy. For the potential energy, you need a datum. You assume that the potential energy is 0 at this level. Okay. So anything above it is positive. So the potential energy is, well, when you are at this position, your mass is at this position, you are this much distance above, it is mgh, so this is h, mgl, 1 minus cosine theta. Okay, so kinetic and potential energies are done. Well, let's take the total energy. Total energy is kinetic plus potential. Kinetic plus potential, which is 1/2 m squared theta squared plus mgl. Okay, the input power is simply, it is rotational, so it is torque times the angular velocity, which is torque times theta dot. So time rate of change of energy, we take the time derivative of this expression, theta dot squared. We use the chain rule. 1/2 goes away, ml squared theta dot the double dot. Now we have the mgl term. Mgl term is a constant, so its time derivative is 0. Mgl cosine theta. Mgl cosine theta is a time derivative of cosine minus cosine theta is sine theta, so it is mgl sine theta times theta dot. Is equal to power input power, which is equal to 3 times theta. As we see, we have theta dot terms in all of these, which get cancelled. And we get the same equation as above. Well, ml squared theta double dot plus mgl sine theta. And then we say that this part is approximately equal to theta. For small oscillations of the pendulum, like up to 30 degrees or so, you can represent it by a linear equation, approximately. Okay. Otherwise, you have to use the sine function. but then the differential equation becomes very hard to solve. It is a nonlinear differential equation. Okay, so one example I gave you was translational. The other was rotational. So let's try to give an example in which we combine them. So let's have another example in which we will have both rotational and translational motions. So there's a spring, which represents the elasticity of the cord, let's say, K. This is R. This is M. This is a pulley of inertia of I naught. So this is let's say that this mass moves with a deflection of x. Now for the spring, this is a little bit complicated. Let me explain. The spring, let's say, suppose that this is L0 for the spring. And then you have a delta here. And then from this delta onwards, the cord is inextensible, so it deflects with x. Maybe I should just try to draw this a little bit better so that it doesn't confuse you. Okay. It's not again a very good drawing. Okay. Something like this, okay? L0, what is L0? L0 is the unstretched position or length of the string. And delta is the static deflection due to the mg. There is a g, by the way, we didn't that. And x is the deflection of the mass. And as you see, the x is measured from the static deflection point. So as you know, you can find that delta quite easily. In statics, k delta K times the static deflection should be equal to mg. Therefore, delta should be equal to mg over k. You can find that distance. Okay. Well, now we want to find the equation of motion for this. One thing is you have to take care is that you have to write draw the free body diagrams for Newton's method. And for the free body diagrams, you have to define the displacements. Let me define the following. Okay, so that actually x plus delta is y. So you might want to measure the y displacement, well, without the static deflection. So this is the deflection of the spring without the static deflection, okay? Deflection of the mass without the static deflection. So let's try to do it without the static deflections first. So we use Newton's method here. Now we have two things. One is we have to write the forces, by the way. So there are Rx and Ry. These are not too important, but let's put them. The spring force that comes here is Ky downwards. And on this side of the pulley, you have a tension force, which is unknown. Okay. So these are all the forces on this thing. For the mass, you have mg, you have the tension. Oh, by the way, I didn't put that there. There was a force effort. So there's an effort here. Okay, these are the free body diagrams, as you see, of both the pulley and the mass. We have to write equations for each of them now. For the pulley, we write a moment equation because it's rotational. Let's do this clockwise. And this distance is r. Tr minus ayr equals IO times alpha. Yes, that's for the pulley. And for the mass, you have summation of the forces in the y direction, downward is positive here, is equal to f of t plus mg minus t is not zero, of course, because this is dynamic. This is ma, which is my double time. And this is, by the way, I0 alpha is I0 theta double dot. Okay. But there is one more thing. We need a kinematics equation which connects y displacement to theta, y equals r theta. This is a no slip condition on the if y is equal to r theta, then y double dot would be r theta double dot. And theta double dot would be y double dot. See? So from here, we can combine our equations. The first one, for example, becomes TR minus KYR equals I naught theta double dot, which is y double dot. Or you can say that T is equal to the tension in the cord is I naught over R squared y double dot plus K1. Okay. This T was an unknown, but we solved it in terms of it and substitute into the mass equation. So we get what? Okay, we just substitute this into here, minus, this goes to the other side as plus, and y double dot plus y double dot plus K1 equals f of t plus mg. Or we can write m plus m1 there is an mg term. We are, well, it looks like we are done, but maybe we are not. If you use the coordinate y, this is what we get. But the coordinate y, as you remember, is x plus delta. So let's continue. Y equals x plus delta. In which case, delta is a constant, okay? It is mg over k, so this is a constant. So y double dot would be if you take two derivatives, would be x double dot because delta gets deleted there. So if you substitute this into the following equation, you get m plus r squared y double dot. Y double dot is x double dot. So I will write x double dot plus k. Now y is k x plus k delta equals, this is x plus delta is that. So it is f of t plus mg. Okay. But what did we say? We said that k delta was equal to mg. Remember that for the mass in static equilibrium, mg was equal to k delta. Okay. So these are the same. So they cancel each other. So we get rid of that mg term nicely. So we can write our equation of motion as m plus I naught over r squared x double dot plus kx equals f of t as our equation of motion. Okay. So the moral here is that if the, let me write this down, if the motion of the mass is measured from effect gravity, which is the mg term, let's say, can be ignored, let's say, because it gets cancelled in the equations. Okay, so you can treat this problem as if there is no gravity, only that you have to measure everything from the static equilibrium. That is, you have to use a coordinate system that measures things from the static equilibrium. Okay. All right, so much. Well, this is the Newton's method. I will continue with the same problem with energy method, but let's take a break because we are getting, it's almost 9:30 now. So let me pause. Okay, so this problem is exactly the same as this one in terms of the static deflection point. That's what I was saying. With the y coordinate, the equation of motion is going to be my double dot plus ky equals mg. But if we don't like this, mg term is a constant term. We might want to avoid this, or you can write this as mx double dot plus kx plus k delta equals mg. As you see, k delta is mg. So these cancel each other. So you get mx double dot plus kx equals 0, which is well, more, it's a cleaner expression than this one. So usually we prefer this one, in which we sort of eliminate the effect of gravity by making a coordinate change, coordinate transformation. Okay, that's basically what we have done. Anyway, this is the Newton's method. Let's try to use the energy method with the same problem. With the same problem, meaning this problem, okay, not the simple one. I mean this problem. In the energy, the disk has a kinetic energy and the mass has a kinetic energy. Each of them has to be written down. So the kinetic energy is 1/2 I/O omega squared, supposedly, plus the mass, 1/2 and x dot squared. Let's say that we use the coordinate x. But x and omega are related. Omega is actually theta dot, change of angles in the disk, and that is equal to x dot over r, as you can imagine, as you can see. The potential energy is easier. Potential energy, well, since we have absorbed the effect of gravity, we just have the elastic potential energy, 1/2 kx squared. We are using the x coordinate, so we don't need the mgh term here. And the input power is F times the velocity is F times X dot. So the energy is, the total energy is 1 over 2 kinetic plus potential IO omega squared. Omega is X dot over R squared. Plus one over 2 kinetic squared. We write dE dt time derivative is equal to power input. So let's take the derivative. This thing goes here, so I naught dot over R squared times the derivative of X dot time derivative, which is X double dot, plus M X dot X double dot plus the derivative of 1 over 2 kx squared is kx times X dot equals power in, which is F times X dot. As usual, these X dot terms cancel. And we are left with the equation, which is the same as the previous equation, m plus squared x dot kx equals me. Which, if you look at it, this equation and that equation are the same. Okay, the equation at the top and at the bottom are the same. Do you have any questions about this? Well, I will be giving you some problems to solve so that you can practice on them. But this is enough for the time being. Let me talk a little bit more about the modeling here. We said that our basic model one degree of freedom model is the following. You have kind of a wall, a spring, a damper, and a mass. This mass is on, well, like a cart or something, and there might be an external force. Okay, this is our model. This is the representation of our system. But, well, actually, this, unless you basically, you construct it intentionally, you will never have such a, mass spring damper system in real life, okay? This is a representation. A real system is not made up of a spring, a damper, and a mass, but it contains all these elements by different means. For example, it contains some elasticity, that is, the materials you use are deformable, so that they have some sort of a spring effect. And the materials obviously have some mass, and also the environment and the materials have energy dissipation. So if you have, for example, I don't know, the wing of an airplane, for example, something like this. Let's say this is the airplane's wing. Well, this can, as you can see in the airplanes, this can vibrate up and down like this. It has a mass, it has a spring effect. Let's say this is the plane. This is the wing. We represent it, and it also has some sort of aerodynamic damping and also some forces acting on it. We can represent this system by the following mass spring damper system. Okay, there might be wind coming on it and so on. And you see the up and down, the vertical vibrations of the airplane wings is a typical, for example, vibration problem. But there is a degree of complexity in which we build our models. For example, you might decide to use, I don't know, let's say, a very sophisticated finite element model like this. You divide it into very small finite elements. In which case you will have a, well, very high degree of freedom system. This is a, sophisticated or complex model. Or you can just use the following. Again, you might use a mass, a spring, and a damper. This is the simple one. Obviously, this one will be more accurate. Okay, and the simple one won't be that accurate, but it's for the time being. If you want a very basic result, like the first resonance or something, this might be okay. So how do we model the spring effect, for example? So the elements are here. Stiffness, which is K. The inertia, which is M. And the dissipation, which is B. Okay. But let's go through them very quickly one by one, especially the stiffness, because the stiffness is kind of important. For stiffness, for example, let's say that you have a bar. Right. Okay. Which is pulled by, this is basic strength of materials knowledge, as you know. The bar has an area of A, has a length of L, etc. You know that if you pull the bar in tension, this is a bar in tension. In this case, the displacement delta is given by FL over A times E, where E is the modulus of elasticity, as you know. Now, we can, represent the bar with a spring like this one now, if you want. It is an axial spring, K, with forces on it, F. This is our model of the bar, where F is equal to K times delta. And as you see, you can see that F is equal to AE over L times delta, right, from this equation. Therefore, this thing has to be our spring constant. Okay, so K is equal to AE over L. In this case, the spring constant of the bar is AE over L. It's not a spring, but you can treat it as a spring, as you see. Similarly, if you have a torsional bar, like here, let's say you have a T here and T here, and this rotates with theta, let's say. Again, we can represent this by a torsional spring, KT. This is again from strength of materials, remember T over Tj. And if T is equal to KT times theta, then the torsional spring should be T times J over. J is the polar moment of inertia. G was, actually, I don't, shear modulus of elasticity, right? And kind of, I forgot these years ago. But it's not just this. We might have, for example, a bar in bending. So this is torsional bar. Torsional. You might have a bar in bending or a beam in bending with a simple support, let's say, like there. And there might be a force on it. This is distance A, this whole distance is L, and so on. So, as you know, this thing is going to be a displacement like this one. And this is exaggerated, of course. This is delta. Delta is going to be, by again strength of materials knowledge, from which you can say that K is equal to there's an L here, 3EI M divided by so the spring constant at A, let's say that this point is where the force acts is A. So so this is a simple support. You might have a cantilevered beam like this. On top of it, so it will deflect like this, again, kind of exaggerated. This delta is going to be FL over 3EI, so that the spring constant is going to be 3EI over time. I is the aerial moment of inertia of the cross section, remember. Okay. So this is a cantilever. And so you can represent lots of systems with different springs, if you need to. So on top of that, you might sometimes have parallel springs. For example, you might have, well, something like this. So it is K1, K2, K3. Obviously, these springs make the total system stiffer. So if you find the equivalent spring of this, say equivalent, let's say, again, KE is going to be the addition of these springs, K1 plus K2 plus K3, or in general, KE is simply sigma Ki, right? You can, that is physically very intuitive. And it is also quite intuitive that if you have series springs, well, something different is going to happen. Because the softest spring will dominate this, as you can guess. So K1, K2, K3. And if this is equivalent to something like this, again. Well, KE is going to be, as you might remember from somewhere, 1 over K1 plus 1 over K2 inverse. So in general, KE is rather, sorry, 1 over KE. One over KI. So this is, springs are just opposite of electrical resistances. As you might remember, in the electrical resistances, you add the series resistances and you add the inverses of the parallel resistances. For example, let me give you another example here. If you have two bars connected like this, let's say this is, you have two, this is a one bar, you have a thinner bar like this to it, and you apply a force on it. Okay. So this one has A1 and E. This one has A2E. Lengths are, this is L1, L2, this is L1. So the K1 here is A1E over L1. And K2 here is A2E over L2. And you can guess, these are series, springs in series. So the equivalent spring, K equivalent, is going to be 1 over inverse of these. So L1 over A1E plus L2 over A2E, which what happens? First of all, E is common, E goes up. So it is E over For example, in this case, since E is the same, they are of the same material. Okay, so this is the equivalent spring of a bars in series. If these bars were in parallel, then you would be adding up their springs. Okay. So we talked about stiffness a little bit. Let's talk about inertia a little for a while. First of all, inertia can be, as you see, it can be translational. Just a second. Just a second, sorry. Okay, I'm sorry. Let's continue. So there is translational and rotational inertia. Well, there might be a combination of that, as I have shown you. For example, you might have the following system, which is the very simple mass. This has a mass of m and a inertia of I, let's say. And we assume that if you assume that there is no slip here, the coordinates are, this is x and this is theta. Then if this is r, if as a radius of r, the kinematic relationship is that x equals r theta, which means that x double dot is equal to r theta double dot. In this case, it's quite easy to, well, I have done it actually before. You can find that the equation of motion is m plus I over r squared x double dot plus kx. Okay. And this will be our equivalent mass for the x coordinate, let's say. For the equation of motion, you can find the equation, well, equation of motion like this. Well, more importantly, I want to do something here. You see, we assume that the springs have zero mass, okay, which is not exactly true. First of all, springs do have mass. Secondly, we assume that, for example, such springs in which you have beams, for example, have zero mass as their spring equivalent. Well, as their spring, yes, as their spring equivalent. But we have to put some mass on them in order to find their vibrational characteristics. What happens here? So we want to find out what kind of mass do they have, or what should be the equivalent mass for a spring. Let's say that we have a spring. Okay. Which has a spring, and it also has a mass of m. Okay. Now this is a little bit difficult. Let's say that the spring has a length of L. And we don't have something on top of it. Now this spring has at this end, it has a velocity of v. And the displacement of the spring at some point, at any point, the displacement of this arbitrary point, we call it x. Okay. It is x. Now we want to replace this by a spring and a mass. This will be, well, it won't be the mass, exact mass, but the equivalent mass. And this will be the spring constant. What is m equivalent equal to? Well, the equivalent mass, is it equal to the spring mass of the spring? Well, no, because some of the mass does not move at all. Is this equal to m? Let's solve it here. Probably not. The answer is no. But what is it then? Okay, well, it's not very easy. Let me try to show you this. Let's say that this is the length of the spring, okay? This is 0, this is L. This is the velocity of the spring as a function of x. So at this point, the velocity is v. We will assume a linear distribution of velocity along the spring, okay? So we will assume that this will be the velocity distribution. Supposedly it is linear. So you can say that v of x equals x over L times v. Okay, v is the velocity at the bottom. So it's a linear variation inside the spring. But this is important because the velocity of one end of the spring is 0, this end, because it's fixed to the wall, like here. And this end is like v. It's hard. And in between, well, we don't know, but it is most logical to assume that it is the variation is linear. Now the critical thing is to find the kinetic energy of the spring. If we can find the kinetic energy of the spring, we can, determine the equivalent mass from 1 over 2 mv squared. Let me do this. I guess, why is that? So the kinetic energy is, as you know, it's 1 over 2 mv squared for a particle. But here you have a distributed thing. Like here, velocity changes all over the place. So if this is x, the velocity here would be x over L times the v of x, well, I should say v of x. And maybe not to confuse you, let's call it VE and VE here, okay. The endpoint of endpoint, let's say. Yeah. So kinetic energy in this case is going to be, this is VE. It is going to be, if you have a small mass here of dm, it will be the integral of 1 over 2 v of x squared dm from 0 to L. Okay. Do you understand this? We are adding up all these small contributions to kinetic energy. So this will be 1 over 2 integral 0 to L of v of x squared over L squared dE squared times dm. What is dm though? This might be a little bit difficult for you, but dm is simply the ratio of the x distance to the L distance multiplied by dx. Sorry. It's not x, of course. It's not x. It is m over L. Yeah. Yeah, it is m over L. Which means that it is density, length density times the small, very small distance dx. Okay. So we substitute that in. Kinetic energy is therefore 1 over 2 integral 0 to L of x squared over L squared squared dm, which is m over L dx. L cubed goes out, VE squared goes out. Am I correct here? I think so. There's m here. So times x cubed over 3 L cubes cancel. So the kinetic energy is 1 over 2 times m over 3 times v squared. It's interesting. This is, as you see, this is, if you want to, if it were a particle, this would be the mass of the this is the equivalent mass. So M equivalent for the spring is simply M over 2. This would be the mass. If the mass were concentrated at the bottom, okay, the equivalent mass would be 1 over 3M. So the equivalent mass of a spring is, if the mass were concentrated at the bottom, its mass would be 1 over 3. Well, 1/3 of its original mass. Okay. So, for example, if you have a spring with K and M connected to a mass with a capital M, okay? If you want to model this with a spring and a mass here at the bottom, and you want to lump the mass of the spring to the main mass, you don't lump it as M, but you lump it as M over 3. Okay. So the equivalent mass of the spring goes down as the 1/3 of its original mass. Well, we did it by doing some kind of integration here. That kind of integration can again be done for other systems as well. For example, if you have a beam with a mass of, well, K and M, the beam has a equivalent mass of equivalent spring constant of K and M here, and let's say that we have a displacement of X here at this mass point. So we want to, express it as a mass and a spring system. This is M equivalent. This is K equivalent. Okay. We found that, as you might remember, the K equivalent was 3EI over L cubed in the previous example. The equivalent mass, well, I'm not going to derive it. If you go through this integration business, it will be M plus, it will be 33 over 140 M, which is M plus 0.236 M. So the beam's mass does not contribute as a whole mass, but only 23 or 24% of it contributes to the to the equivalent mass, as you see over here. Okay, let me give one more example, then I guess I have to stop because there is no more time. Let's say that, no, it's not. Let's have a simply supported beam. Let's say that we have a mass, and that mass is carried by a shaft just in the middle of the shaft. So it is simply supported like this. This is just in the middle, so this is a lower. This shaft has a mass of M, and the displacement here is X. Again, we want to replace it by an equivalent spring and an equivalent mass. You can find it true strength of materials, that the K equivalent is 48 di over L cubed. And the equivalent mass is this mass, which is M, plus 0.48. So in general, we can reduce a system, let's say, a complex system to a single degree of freedom. Of course, this is not correct. This is approximately. Using a K equivalent and M equivalent, this kind of approach usually works well. It works, of course, it can be a good approximation, it can be a very crude approximation, but it's a starting point, okay, in the analysis. If you want to do, more accurate analysis, then you have to go to multiple degree of freedom systems. You have to go to finite elements. You have to go to, well, maybe, more advanced techniques, which we will not be discussing here. We are just doing the very basics. Okay, well, there are things I want to talk about, but time is up, so I have to stop here. So let me stop the recording.